Any questions? This business of fermions is, I think, quite confusing, at least because it's so new. I mean, I think that our grandchildren will take Grassmann variables as old hat. They'll learn it in high school, and they'll look forward to questions about them because the integral table is so simple. By the way, differentiation and integration are essentially the same with Grassmann variables. Let's see if I can say that. Suppose f of theta is a plus b theta. Then the integral of f of theta d theta is equal to b. The derivative of f of theta d theta is also equal to b. This is obvious if b is a complex number thing. If b is Grassmann, then this is correct if you're differentiating from the right. Okay. Otherwise, it's minus b. So left and right derivatives are different if the b itself were Grassmann. Okay. Last time, what we learned was that if we had a function of a matrix that was e to the minus, let us say, theta dagger a theta, and then we had d theta star 1, d theta 1, dot, 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 d theta n star d theta n, then this was equal to determinant of the matrix A. Here I'm thinking of A as being a complex square matrix. So we proved that for the 2 by 2 case last time, and I'll just say it's true in general. Now, remember that we got this integral table by saying that we wanted to have shift invariance. That is to say, we wanted the integral of f of theta plus zeta d theta to be equal to the integral of f of theta d theta. Now I'll show you why we actually want that. Suppose we have the following. An integral e to the minus theta dagger a theta plus theta dagger zeta plus zeta dagger theta. And then I'll just say, can I say d theta star d theta just to mean this product so that we don't have to write it this way every time? Okay. And I'm thinking here of, inasmuch as this is even, I'm thinking of zeta as being Grassmann. Now, here's what we can do. Since this thing is invariant under displacements by theta, we can do the following. We can say that this is the same thing. Maybe I can do it here. It's the same thing as e to the minus theta dagger a theta. A, of course, is a matrix. Theta is an n vector, a Grassmann variable. And what I'm going to write here is not theta, but rather theta, and we're going to displace it by A inverse zeta. And then the next one is going to be plus theta dagger zeta. We're thinking here of theta and theta star as independent variables. You know, when you have complex variables, you can think of the real and the imaginary part, of course, are independent. You could also choose to think of Z and Z star as independent, and that's an equivalent calculus. So here what I'm shifting is theta, but not theta star. And so the next one is plus zeta dagger, and now this is theta plus A inverse zeta. And now we're doing d theta star d theta. Okay. Well, what has happened here? Of course, I've assumed that A is an invertible matrix, so A is non-singular. We have here plus zeta dagger plus zeta dagger theta, and over here, all right, let me get this straight. Did I screw up? Hold on. Okay, yeah, here we have minus theta dagger A times A inverse zeta. So this is minus theta dagger zeta. That cancels this one. So this is then equal to e to the minus theta dagger A theta plus zeta dagger theta plus zeta dagger A inverse zeta d theta star d theta, where the last term came from this times that. Okay, now we're going to shift theta dagger. And so this is e to the minus theta dagger plus zeta dagger A inverse A theta plus zeta dagger theta. And notice there's only one theta star here, so we've just shifted once. And then we have this term, which is zeta dagger A inverse zeta d theta star d theta. Okay, now you see the A inverse cancels, and we have minus zeta dagger theta. That cancels this one. So this whole thing is equal to integral e to the minus theta dagger A theta plus zeta dagger A inverse zeta d theta star d theta. And now this is independent of theta. This thing is the determinant. And so this whole thing is equal to determinant of A times e to the zeta dagger A inverse zeta. And let's just remind ourselves what that is. That is what we started with, which was e to the minus theta dagger A theta plus theta dagger zeta plus zeta dagger theta d theta star d theta. So this quadratic form turns out to be that. So that's a generalization of this relation. And this is a formula that's useful when you're trying to do perturbation theory in terms of Grassmann variables. Okay. Now we're going to go from a finite number of Grassmann variables to a, that is to say, a finite number of fermionic variables and a finite number of Grassmann variables to a fermion field and a Grassmann field. And so the extension is that we now have psi sub m. I'm sort of using the Dirac four vector here. So this anti-commutator is delta m n delta of x minus x prime. And on the other hand, psi m of x and t. These are equal time anti-commutators. So these are the fermion operators. Let me see if I might have a different chalk here. Oh, damn it. This chalk doesn't. All right, let's just let the thing run. I'm going to see if I can get better chalk in my office. Okay, this chalk is better for these blackboards. Okay, we'll also have, of course, some new Grassmann variables. You see how much better the chalk is. This is the Mexican chalk. Chi m of x. And now I'm thinking of this as, well, I guess we can put a t in there. So this will be, well, I mean, they're going to anti-commute at any, there's no need for equal time commutators when we're talking Grassmann, everything anti. The Grassmann variable is anti-commute with everything, except ordinary things like complex numbers. So they commute with complex numbers. Now we're going to define a, we can imagine there's some state S. Well, one problem with this chalk is that it's soft, and so it breaks easily. So let's suppose that S is not annihilated by any of these fermionic operators. Then we're going to define the ground state as the product over all m and over all space points of psi m of x and let us say times 0. 0. That was a 0, not theta. We don't want to grasp in time. Although in supersymmetry, one way of thinking about it is you take ordinary space-time and you extend it to a fermionic space-time. So let me just write this more clearly. Product over m. M goes from 1 to 4. Okay, I'm thinking of a single fermion field. All space points, psi m of x, and I'm defining this at time 0. So it's all of this acting on this state S. And that's what we're taking to be 0. So there's a certain arbitrariness about this, namely what the S state is, just as there was when we had just a single Grassmann variable or a single pair of Grassmann variables. Okay, and this obviously is a state such that psi m of any x, also times 0 on 0, is going to give us 0, because when we multiply by psi m, there's going to be one of these space points and one of these indices m will correspond to this one, and so we'll get 0 because psi m squared is 0. Okay, well, the coherent state for here is going to be exp of integral and sum over m, and it's going to be psi dagger m at x and 0, let us say, chi m of x minus a half chi m star of x chi m of x d cubed x. So explicitly it's that. And then of course that's an operator. It acts on this state 0, which I've just defined. And another way of writing that is to say that this is e to the integral psi dagger chi minus a half chi dagger chi d cubed x on 0. And then what you can show is that chi m of x, well, x and 0, times 0, acting on this state chi, in fact, is equal to chi m at the space point x, the state chi. Okay, so are we sort of happy with that? Now, these things have much the same properties as for the case of one variable or a few variables. Namely, this inner product is e to the integral chi prime dagger chi minus a half chi prime dagger chi prime minus a half chi dagger chi d cubed x. So that's the inner product of two of these fermionic coherent states. Now, there are many ways you can reshuffle these three terms in the exponent. You could, for example, take this plus sign and combine it with this, and in other words, you take this, effectively there are two of these because these are 1/2. Multiply by half, you have two of them. You combine one of them with that one and one of them with that one, and you can rewrite it in various ways. One of the ways that you can rewrite it, and let me just mention that here, is e to the integral a half chi prime dagger minus chi dagger chi minus a half chi prime dagger chi prime minus chi d cubed x. And you may find that you can see that this part is a direct combination of these two guys. But this one is a direct combination of these two guys, but then we switch the, instead of having chi minus chi prime, we have chi prime minus chi. Okay, anyway, this is just arithmetic or algebra. We have an identity operator for this case. The identity operator is an integral chi d chi star d chi. And of course, this thing is the same thing. Oops. Chi, and it's basically product over m and space of d chi m x star, well, d, just ordinary d chi m x. Always, it makes sense to pair the two, the Grassmann differential with its conjugate. Then you don't have to worry about the order. All right, well, the next step, I mean, you see this coming. We have to know what is a Hamiltonian for the actual fermion field. And this is always a little bit surprising. Namely, it's psi bar gamma dot grad plus m psi d cubed x. And so let me just emphasize that the Dirac Hamiltonian does not have psi dot in it, which is something that is a little bit surprising. I'm using, as I said, Weinberg's metric with Schwarz's metric. I don't know, there might be a minus sign. Yeah, there'd be a minus. Well, no, actually, since I'm doing things in three-dimensional notation, this is even PAM Dirac's Hamiltonian. So this nothing wrong with that. All right. Psi bar, let me just remind you that psi bar is equal to I psi dagger gamma 0. And I am using Weinberg's gammas. So we have gamma A, gamma B anti-commutator is 2 eta AB. Of course, this is also Schwarz's convention, but Weinberg has eta to be 2 times minus 1, 1, 1, 1. And that's probably a better choice of metric, although p squared is minus m squared with this method. All right. We've seen that psi on chi is chi on chi, and chi prime psi dagger is chi prime dagger. And so if we take this matrix element chi prime e to the minus I epsilon h0 pi, and here of course epsilon is, you can think of this as machine epsilon. What is it that the computer scientists talk about, the smallest number the computer can compute?
Machine 0, I guess.
Huh?
Machine 0?
No. It's I think they call it machine epsilon. Okay. Anyway. Okay, so small number epsilon here. What is it? Well, inasmuch as this is this coherent state is an eigenstate of psi from the right, and chi prime is an eigenstate of psi dagger from the left, it turns out that this thing is effectively, let me write it in 2 steps then. It's chi prime e to the minus I epsilon, and now I'm just going to rewrite this as chi bar prime gamma dot grad plus m chi d cubed x pi. So in other words, we replace the operators with their eigenvalues, and now we're going to write the inner product chi prime chi of those 2 coherent states. I'm going to write it in this funny way, and so put in the epsilon, and so what we've got is an integral E integral, and now this is a half chi prime dagger minus chi dagger chi minus a half chi prime dagger chi prime minus chi. So this is just the inner product of the two coherent states. And then minus I epsilon chi bar prime gamma dot grad. This is 3 vector, of course. Plus m chi, all of that d cubed x. And that's it. And now we're going to do this trick where we say, over here, we're going to say chi prime minus chi is going to be, and we're going to call that epsilon chi dot. Okay, this is what we did with the path integrals earlier. And similarly, over here, chi prime dagger minus chi dagger is going to be epsilon chi dagger dot. And when we do that, what we've got is integral. Wait a minute, what is this integral? Boy, that's dumb. What a huge typo. Okay, there's no overall integral, obviously. The integral's in the exponential. Wow. And it's the biggest typo. That were a roach, it would be scary. So let me, yeah, it's funny, the best way to find the typos is to teach the subject. Anyway, so this is then an integral of, in fact, we can pull out the epsilon, and then we have a half chi dagger dot chi minus a half chi prime dagger chi dot minus I chi bar prime gamma dot grad plus m chi, all that d cubed x, and it's of course in the exponential. So everything multiplied by epsilon, and everything is inside this box here, and I guess I'll have to write the dots a little more clearly. Okay. Now, everything in this exponential is proportional to epsilon. So at this point, we're going to you see, this chi bar prime differs from chi bar by something of order epsilon, and so we're going to erase the prime here and the prime there, and so what we can say is that well, maybe I'll do this. Maybe I have enough space here. Chi prime e to the minus I epsilon h0 chi is then another superfluous integral sign. It's a half chi dot dagger chi minus a half chi dagger chi dot minus I chi bar gamma dot grad plus m chi d cubed x. Okay, so that's our inner product of a tiny time translation operator. And now what we do, of course, is we string together a large number of these. Well, let's do 2. No, actually, I go immediately to a large number. So we then have chi at some later time, e to the minus 2it. I'm imagining t as being a big number, like the age of the universe, or half the age of the universe. H0, chi minus 2. And this now will, this integral sign is now genuine because we had to insert complete sets of states. In other words, we're using this identity operator over and over and over again. And so what we have then is e to the integral a half chi dot dagger chi minus a half chi dagger chi dot minus I chi bar gamma dot grad plus m chi. And now, notice we're thinking of this as dt. And so when we add them all together, we have d fourth x, and this d fourth x is taking us from minus t to plus t, as well as overall space. And then finally we have d chi star d chi. Okay, so that's the expression, and if we integrate this by parts, drop the surface term, we just get integral e to the integral minus chi dagger chi dot minus I, whoops, chi bar gamma dot grad plus m chi d fourth x d chi star d chi. Okay. And now, in fact, this structure here, minus chi dagger chi dot, well, this is equal to minus I times, I have a minus sign over here. What is chi? Chi bar is an I here. I seem to have a minus sign, which is the last thing I want. All right, let's just try to get this straight. Minus chi bar chi dot is what I seem to have. And this is minus I times minus I. Oh, gamma 0 squared is minus 1 in Weinberg land. So in Austin, Texas, gamma 0 squared is 1. That's a minus I. So I have minus I, and so I can make this a plus I, chi dagger gamma 0 squared chi dot. Okay. So this turns this into minus 1, minus I is minus 1. Okay. So now altogether this is minus I chi dagger gamma 0, that's chi bar, and then gamma 0 chi dot. So that's our expression there. And so then what we have here is that the argument of the exponential then is the argument of the exponential is I, so let me just do this whole thing, I times minus chi bar gamma 0 chi dot. So I've written this sort of in a backwards way. I've commuted the minus sign through the I. And then the rest of it is up here, which if there's an I here, it's just minus chi bar gamma dot grad plus n chi d fourth x. So I'm just doing this exponential, the argument of the exponential. And now you see what this is. This is actually I integral minus chi bar gamma mu d mu chi plus m chi d fourth x. Okay. Yes. Okay. And so this is what we call the action. So in other words, what we have then is chi at a later time, e to the minus 2I, huge time here, H0 Dirac, chi minus t. And these guys are just labeled. So this is just a particular coherent state labeled by a function chi minus t, and this is another coherent state labeled by chi t. This is then integral e to the I, and then this is just L0 Dirac d fourth x d chi star d chi, or equivalently it's e to the I S0 d chi star d chi. So that's of course what we wanted, namely that the amplitude is an integral of the action. The fact that all this works out is kind of amazing, and as I said, people will eventually get used to this and think of it as natural, whereas just between you and me, I think of it as pretty amazing. All right. Now, as you know, the time-ordered product of two fermion fields, or one fermion field with itself, this is the first term is the natural thing that would have to be there. But then we put in a minus sign here. And we do that because these Fermi operators anti-commute, and so we don't want some huge discontinuity when the time flips from x0 being later, x1 being later than x2, and so forth. So we can go back to this path integral. What's the path integral? Well, the path integral is this is equal to that. But if we imagine that we're back here where we're slapping together a large number of these e to the minus I epsilon terms, then we could equally well, in between these, we could stick in fermion operators. And then those fermion operators would hit the coherent states at intermediate times and just turn themselves into Grassmann functions. And so what this means then is that time-ordered product then of, let us say, psi bar x1 dot 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 psi of x2n. It's in general, if you're taking a mean value of fermion fields, you want an even number of them, so that what you've got is the mean value of something that's even. And then this is then equal to an integral. So this is the ground state, chi double prime, and then we would have chi bar of x1 dot 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 chi x2n, and then we would have e to the I s0 of chi, this chi being an integral over d4 x, or not in chi being an integral, but chi depending on d4 x, or chi being the sequence of the coherent state arguments for all the intermediate state dyadics that we put in. And then we would have chi prime 0, and then this would be d chi star d chi, where we're integrating over chi prime, chi double prime, and all the chi's that go from chi sub minus t to chi sub plus t. And then this is divided by integral e to the I s0 chi d chi star d chi. And I've left out, hold on, I've left out two things. I have to put this in there. This would be 0 chi double prime, chi prime 0, and then d chi star. Okay, so this is the fundamental rule that you can imagine that we derive. Should I put a little more detail here? We okay? All right. Okay. And these terms here will effectively insert an e to the minus chi. This one would be something like e to the minus chi prime dagger, chi prime star chi prime in some sense, some quadratic form in chi prime. And this would be some quadratic form in chi double prime. Those would lead to the I epsilon, the correct I epsilons, just as they did for bosonic fields. So I'm sort of skipping that. And the next thing is just a direct application of this formula, is that we can define z0 of j. Now in the book I wrote this as z0 of zeta, but I think really there's a limit to how many Greek letters we want, and pretty soon it just gets too confusing. So this is actually a Grassmann variable. That's why I chose zeta, but let's just think of it as a Grassmann j. So I'm defining this to be vacuum time-ordered product e to the I integral j bar psi plus psi bar j d4 x 0, and now that's this ratio here, In other words, it is integral e to the I integral j bar psi plus psi bar j plus S0. Oh, I've switched from chi to psi. Well, what are we going to do? This is a d4th x, actually. And then S0 has the d4th x built in. So this is d psi bar d psi over e to the I S0 d psi bar d psi. So I meant to write chi, and this was a slip of the. All right, so imagine that they're all chi's except for the j's. All right. Okay. I think maybe I should just put in a few more lines as to how we go from here to the Feynman propagator. I was doing this afternoon, and I may have a minus sign loose here, so it's basically the same idea as in the case of boson fields. We did it for the scalar field in detail maybe a week ago. And so here, okay, so let me try to do this. So what we've got here is an integral of let us say j bar chi plus chi bar j. So I'm pulling out the I, and then there'd be an I S0, so I can pull out all the I's. So this is then plus the S0, and S0 is that minus chi bar gamma mu d mu plus m. And I can put a minus I epsilon here, chi d4 x. So that's the argument up there. And so what we're going to do now is write everything as a Fourier transform in order to diagonalize this. And so this will be it will be j tilde bar, or j tilde complex. Well, actually, this is bar. Chi tilde plus chi tilde bar j tilde, and then minus chi tilde bar, and now this is a p. And so this is I gamma mu p mu, because the derivative brings down an I p mu plus m minus I epsilon chi tilde. And now what we have is d4th p over 2 pi to the 4th. And now we make a shift. We set psi tilde of p equal to chi tilde of p minus j tilde of p divided by I p slash plus m minus I epsilon. If you want, you can sort of blow away the minus I epsilon there. And now, in effect then, we're setting chi equal to psi plus j tilde over this structure. And when we do that, what we get here is integral j tilde bar psi tilde plus j tilde over I p slash plus m. I'm going to leave out the IFs one. Plus psi tilde bar plus j tilde bar over I p slash plus m. That's that times j tilde of p, say, just to keep that straight. And then we have this structure here, which is chi tilde bar, well, no, psi, sorry. So this is psi tilde bar plus j tilde bar over I p slash plus m. And then I gamma mu p mu plus m. And now psi tilde plus j tilde over I p slash plus m. All right, times d4 p over 2 pi over 4. Okay, well that's a little bit sloppy. But what you can see here is that the linear terms in j cancel. So in other words, one linear term here is j bar psi. Well, over here, we have a j bar psi with a minus sign, and then we have this canceling that, and so the thing cancels, the linear term cancels. All the linear terms cancel. And what we're left with then is we have a j tilde bar, j tilde over I p slash coming in once, and then over here it's coming in twice, and actually, now that I think about it, I'm a little bit worried about what happens when we bar this thing and we've got this in the denominator. I sloughed over that when I did the derivation this afternoon. In any event, the linear terms cancel, and what we've got is this once, twice, and then it cancels once because the IP slash and the IP slash and the IP slash all together, we've got 1 over IP slash. And so we've got 1, 1, minus 1, and so there's a 1 that's left over. So altogether then, this is equal to an integral of j tilde bar 1 over I p slash plus m, j tilde d4 p over 2 pi over 4. And then the rest is just the Dirac action in momentum space. So I could write that maybe as just S0, with the understanding that it's either in position space or momentum space. The two are the same. And so what's the bottom line? The bottom line here is that that this Z0 of J, which, oh, well, I can do it over here. That this Z0 of J then is this thing, and so what does that thing turn out to be? Well, it's an integral e to the j tilde bar 1 over I p slash plus m j tilde d forth p over 2 pi to the 4th. That's one term. The other term is plus S0 of psi, and we're doing d psi star d psi. And then in the denominator, we just have the old denominator, which, of course, I wrote here in terms of sine, I meant chi. So this thing is, oh, and there's an I here. Integral e to the I S0 of chi d chi star d chi. Okay. Now, the point is that this, of course, is in the exponential. This thing here is just a number. Grassmann number, but it's just a number, so we can factor it out. Then we have a ratio of e to the IS0 of psi, e to the IS0 of chi, and we're doing d psi bar, d psi star d psi, and down here d chi star d chi star d chi. Well, the integrals are the same because this is just a shift. So those all cancel, and the result is that z0 of j is just e to the integral j tilde of p 1 over I p slash plus m, and I'll put in the minus I epsilon, j of p d forth p over 2 pi to the 4th. So there's a very nice expression which is the parallel, is the fermionic analog or Grassmann analog. Remember, J is Grassmann here. Analog of what we had in the bosonic case. And so then what you can do is you can then differentiate functionally with respect to the Grassmann variables. You will then pull down factors of 1 over I p slash plus m. And over here, that will pull down the fermion fields. And so you get that the time-ordered products of fermion fields are some sort of things involving Feynman propagators. To within a factor of I or minus I, let me get first of all another piece of chalk because I'm basically what we've got then is that this z0 of j, if we rewrite it, it will be e to the integral j bar, which I'm writing it as j bar, and I wonder, is it just j star? In any event, it's essentially this. So if we functionally differentiate with respect to j, we pull down the propagators in position space or over there in momentum space. And this delta of x minus y, let's just see what it actually is. It's minus I integral e to the I p x minus y. So this is doing the Fourier transform backwards, and then we have I p slash plus m minus I epsilon d forth p over 2 pi to the 4th there. And now this looks a little bit funny, and it is a little bit funny. So let's unfunny it. You get minus I integral e to the I p x minus y, and now we rationalize this. I p slash plus m minus I epsilon, and we multiply by minus I p slash plus m, minus I p slash plus m, d4 p over 2 pi to the fourth. And now this thing just gives us p squared plus m squared. So this is minus I e to the I p x minus y minus I p slash plus m over, and now this is p squared plus m squared minus I epsilon d4 p over 2 pi to the fourth. So that's what happens, and so we get the Feynman's propagator, and this is Weinberg's expression for it. In Schwartz, you have a different set of minus signs. Okay. I think the next topic then is to go on to we've only got a few minutes, but I can just sort of warm the thing up for you. The generic action for a non-Abelian gauge theory, minus a quarter f a mu nu f a mu nu, or we could raise the a if we want, anyway, minus psi bar gamma mu d mu plus m psi p fourth x. So what's f a mu nu? So this is d mu a nu minus d nu a mu, and then plus a coupling constant, the structure constants f a b c, a b mu, a c nu. So these are you remember when those of you who took 467 from me when I did group theory, I emphasize these structure constants. And the reason, of course, is that they show up there. The covariant derivative d mu psi is the ordinary derivative minus I g. And then this psi is in some representation. These are the generators in that representation. So it's TA, AA mu psi. Okay, and I guess you've seen this so many times I don't need to repeat it, but if you want, we've got another 4 minutes, I can repeat it. The whole point of this covariant derivative is so that the action is invariant when we set psi prime of x equal to some, I want to say some matrix G, but we've got G as a coupling constant. So let us say M, that's a matrix, depending on x times psi of x. And this part would automatically be invariant without the derivative, so the mass term would be. But the term that isn't is the part that has the ordinary derivative, and to fix that we have a covariant derivative, and the covariant derivative is defined in such a way such that d mu psi prime of, let us say, x is equal to m of x d mu psi of x. And the way that we arrange that is to have, what would that be? D mu, let's use matrix notation. This is d mu, let me just write it, plus I a mu, so I'm writing the covariant derivative this way, plus a mu prime m psi psi should be m d mu plus I a mu psi. Okay. And so this works as long as d mu, see the extra term here is d mu m plus I a prime mu m is equal to m, I think I've got all the terms right. Right, this is okay. And so then what we say is that a prime mu should equal a mu, but we need to get rid of this m, so we have an m inverse here. I want an m on the oh, this had an m. This was, I left out the m. So to get rid of this m on the right, we multiply by a mu, m to the left. We get rid of that one by an m. That is there, okay. And then the rest of it is minus 1 over I d mu m inverse. I think that's right. The d mu m would go over, divide by I, we get a minus sign. All right, I think that's correct. Anyway, to within a minus sign and I. This is the trick that Yang and Mills invented that makes this invariant. Okay, so any questions? By the way, did anybody ask a question and not get a candy? Is anybody particularly hungry? All right, so let's turn it off. Good.